Welcome to the High Energy Density Science Center's. I'm pleased to have with us today Dr. Brown, who is a target design physicist in the Inertial Confinement Fusion Program at Lawrence Livermore National Laboratory. His current work focuses on the intersection of experimental science, high-performance simulation, and machine learning. Brian leads a laboratory-wide effort aimed at developing deep learning methods for many missions. He has designed ICF experiments for almost 15 years, including the first cryogenic layered experiments at the National Ignition Facility. He developed new ICF ignition metrics using the first large-scale ensembles of two-dimensional ICF simulations and data science techniques. Brian completed a PhD at the University of California, Berkeley, where he studied topological methods for high-dimensional dynamical systems. He also holds a BS in Mechanical Engineering and a BA in Liberal Arts from the University of Texas at Austin. When not doing science, he can be found racing his bike or chauffeuring his two daughters to swim and gymnastics. So this seminar will be recorded. If you're uncomfortable with that, please log off. And also, it's an unclassified WebEx meeting, and there are non-lab people and foreign nationals logged in, so please be aware of any export control issues. After Brian's talk, we'll take questions. You can enter your questions in the chat field, and I will read them off. And otherwise, I'm very much looking forward to Brian Spear's talk, and please take it away.
All right, thank you for the lovely introduction, Paul. I appreciate it. I'm really happy to be speaking with this group. It's an exciting field, HED is for us, and the combination of the things that I want to talk about today, cognitive simulation, with the things that we can do in my home field of ICF and the broader field of HED writ large is really exciting. So we call this cognitive simulation, and I'll tell you a little bit about what that is, but it's really combining simulation and experiment with artificial intelligence. And so we'll dig in as soon as I can advance my slide. There we go. So before I dive into what we do with AI at the laboratory, I want to sort of think back to a time when I was a graduate student at Berkeley, and at the University of California, there was a problem then that we wanted to solve things that humans knew how to do, but at scales that they couldn't attack. And so we're going to do the same thing here today. Looking back to the Berkeley problem, there's a problem of a first responder comes into a building, finds a victim incapacitated and trapped under a heavy beam. So a solution could have been, let me send in a robot and take out the subject matter expert. And that was a much more complicated problem than what actually needed to happen, which was enabling that first responder to do what they already know how to do, which is save that person, but equipping them to do so. So the solution back then at Berkeley was put this person in an exoskeleton, let them lift the heavy beam that the victim is trapped under, and now the first responder can take this person out of the building and do all the things that she already knew how to do. So the AI strategy and the AI world is exactly the same. What we need is an AI exoskeleton that can help us attack these very heavy problems. So we don't want to take scientists out of the fight, out of the doing of physics and the understanding of science. We want to equip them with the tools that they need in order to get back into it. So we're doing this at the laboratory here across all kinds of missions. So there are stockpile stewardship missions, infrastructure issues associated with the grid. We want people not to spread nuclear weapon usage around the world, so we invest in non-proliferation. And it's particularly germane these days, the biodefense and health security work that we do. All of these have a real common challenge. They have their own equivalent of the first responder grappling with a too heavy pillar. And that, for us, that's the data and complexity of the information that we're trying to grapple with. Our compute facilities and our scientific facilities are producing information at a rate and at a scale that we just can't grapple with as unassisted humans anymore. And so what we need is a way to navigate that problem. We need the equivalent of the exoskeleton for the first responder, but we need it for scientists to put them back in control of their problem. So At our laboratory, as we think about that problem, we do two things. We advance our understanding by challenging our simulations with experimental observation. And that means we need to be good at simulation or high performance computing. And we also have a pillar of excellence in large scale experimentation, like at NIF. And most of this audience will be familiar with that, so I won't dwell on how we do ICF research at NIF. But when we do that research, we have a model that served us well for years. That is, we compare a few key scalars. We know how to go into a simulation and extract a contour, go into an image and extract a contour, get a few key scalars and compare those, which we can do. And in a long lead time loop, we can compare those, find discrepancy, and go back and improve our physics models so that we can better predict the experiment, do a better experiment, and continue to iterate. But that, as an analyst, as a designer, that leaves me disappointed because we leave lots of information on the table. There's far more information. Sorry about the mouse. There's far more information in this image than the contour that I extract. And so the model that I constrain with it is less constrained than it would be if I had used all of the information. So ultimately what we need are new techniques that improve our predictions in the presence of enhanced experimental evidence, that is using all of the experimental evidence. So since this talk is about AI and machine learning, you'll not be surprised that I suggest we're going to introduce a new pillar, which is machine learning to compare simulation and experiment. And this is our exoskeleton. It is the tool that allows us to grapple with the scale and complexity of data that we can produce by high performance computing and also by large scale experimentation. And the general idea here is that, it's the foundation of what we call cognitive simulation. The idea is that this deep neural network tool is going to be trained on a large amount of simulation data so that the network understands exactly the worldview of our simulations. But that's wrong because our simulations are never perfect representations of the experiment. So now we're going to go back and retrain part of this neural network tool with our sparse and very expensive experimental data. And now I've got a tool that knows the best of both worlds. It understands the general features of the theory that we've encoded from the simulation, but it can make very high precision and accurate corrected predictions to tell us what we're actually going to see in the laboratory. So in that way, machine learning allows us to use our full data sets to make our models more predictive. The drive to make them more predictive is our central challenge here. So to specialize this a bit for this audience in the context of the HED Center, I want to ask ourselves a guiding question. So what would it take to revolutionize the way that HED science data is captured and consumed? And I ask that out of general curiosity and out of self-interest. So you may have heard a talk in the seminar series before by Tammy Ma, who leads the HED Laboratory Plasma Physics program at Lawrence Livermore. And she, I think, has talked about the high rep rate laser science that we're interested in doing. So let's think about what could happen. We could imagine using high repetition rate lasers to select a new optimal experiment to perform 3 times per second and incredibly quickly. So we can imagine an AI model that is sitting inside a control loop that's keeping the laser from damaging itself and pushing to use it to its fullest potential. We can imagine a loop wrapped around that is optimizing the experimental performance. Say we're doing target normal sheath acceleration that can walk us to the highest intensity, most focused particle beam that we can produce on the backside of a target. And even more, we can consider a further outside loop that brings in modeling and simulation, so that rather than just navigating empirically using the diagnostic data, we can have a model in the loop that's saying, here's the place I predict is the next best place to go. You can immediately, a few hundred milliseconds later, do that experiment, measure the discrepancy between it, and then come back and say, okay, here's the next place that I should go that not only maximizes my performance, but also minimizes my simulation error. And if you could run this loop, you have what I like to think of as a knowledge generation facility. We have the supercomputing or the computing and the experiment and the driver all in one tightly coupled loop so that we're both learning how to get the performance that we want out of the physical process, but also simultaneously building up and refining the model that governs that physical process so that both are advancing at the same time. So this is our 2 pillars, the experiment and the prediction advancing, but now that loop with AI guiding it and high rep rate facilities takes a step every few hundred milliseconds rather than once a month or once a year, depending on the scale of your facilities. So that's wonderful, but we need some essential capabilities to take this from science fiction into science fact. And that's what we're going to talk about today. What is the foundation that underlies this? And then we'll come back at the end and take a look at this, and you can think a little more deeply about what all of these loops mean in the context of some underlying capabilities. So the capabilities we need are the ability, as I mentioned already, to use all of the data. We can't leave any of it on the table. That's wasteful and just unsatisfying to us scientifically. We need to quantify the uncertainty in our predictions so that we can do good comparison with our experiments and actually measure the discrepancy in a meaningful way, the discrepancy between simulation and experiment. Once we can measure that discrepancy or the bias, we need to detect and remove that bias between simulation and experiment, both by collecting more data and generating models that understand how to react to it. And then, of course, we got to compute on timescales that are commensurate with the experiment. So we need a compute facility that is capable of thinking and modeling and advancing itself every time that I take a shot, or every few times that I take a shot. In ICF at NIF, I have the luxury of thinking for a few weeks between shots. Not so if you're doing it at 3 Hertz. And then finally, you need optimization strategies that seek out the desired performance. You can shoot your way out of this problem right now. The folks with the fastest lasers in the world can collect data far faster than we could at Omega or at NIF. But there will come a time where you need to use that data most efficiently. Shooting your way out of it won't be enough. You need to not just do the most experiments, but you need to do the smartest experiments. So CogSim brings this within reach for a new class of what we can call self-driving experimental facilities. Okay, from the CogSim perspective, there are 3 foundational advances that we need to transform our approach to predictive science. First, we need improved models that do these things that I've been talking about. They've got to use all the data, they've got to estimate uncertainty, and they need, in as close to real time as possible, to improve by exposure to the experiment data. We need software tools to develop and guide those things, which means we need computational workflows and digital thread to wrap these models together. And then we need computational platforms that can support the advancement of these tools. So if I know how to model it, and I know how to execute that in my compute facility and in my experimental facility, I need a computational platform that can support the modeling and the decision-making that we're trying to do on the timescales that we're talking about. So these advances improve the modeling chain in this setting, but thinking about our larger laboratory, they can do this across programs and missions, and they actually are right now. So just a note of terminology to get us all on the same page. Deep neural networks are becoming old hat, but I want to make sure that everybody is speaking the same language. So we use fundamentally deep neural net models as surrogates to map inputs to outputs. And we can get from inputs, if we're thinking about the laser world, that may be some dimensions of the target that we're going to fire at, the laser brightness that we're going to use to illuminate that target. And the outputs are the things that we can measure: diagnostic quantities, neutron yields, particle brightnesses, ion temperatures, things like that. And we can transform from inputs to outputs in any number of ways. We can do it by analytical theory, we can do it by simulation, or we can do it by deep neural network. And if we do it by deep neural network, then we can look at this picture over here. Deep neural networks work by taking the inputs and making a sequence of nonlinear transformations using layers in that deep neural network. And then they make one final transformation that go from the internal state of the neural network to the output that we can interpret as physicists and humans. So I want to point out in particular these layers that are hidden to you. You see the inputs, you see the outputs. In these hidden layers, there's one distinguished layer, which is the last one before we make a nonlinear transformation to the human world, which we'll call the latent space. That's the most highly distilled and condensed version of the physics correlations that we want to think about as the neural network can understand it. And so we want to think about engineering and exploiting that latent space as one of the key strategies we can use to make our models capable of dealing with the amounts of data and the kinds of data that we're talking about. So we've done this based on a few years of work, actually, in an initiative here at the laboratory and some projects that are following on top of it. And we started by developing a cyclic system of subnetworks that are engineered to produce these required performance features that we're interested in. The first one, and maybe the most powerful one, is using a multimodal autoencoder. So this is a deep neural network that takes your simulated experimental data or your actual experimental data, images, scalars, time histories, and maps it back into itself going through a reduced dimensionality bottleneck in the middle. So we squeeze high dimensional data through a low dimensional space and back out. And in doing so, we develop a representation of the problem that captures the correlations between all of the data that we're shoving into it and gives us this smaller, more compact space from which we can work. So that checks one box. We can use all the data, and we're working on understanding how to engineer this latent space. Next, we want to enforce physical consistency. So we want predictions that look like our training samples. So sometimes what we do is set up a generative adversarial network where we produce a forward model, and we also have a discriminator. And this is a game of sort of counterfeit currency passing. The forward model tries to make up a fake example that's not exactly the training experiment or simulation that it's seen. The discriminator tries to catch it as counterfeit and decide whether that's real or fake. And both of these have to get better in a competition with each other. And when you can make good outputs that the discriminator can't catch as fake, and the discriminator has gotten so good at fakes that are close to the real ones that the forward model has gotten better, then those two come into equilibrium and we can move on. So that gives us a degree of consistency with our physical data. And then we need to enforce a notion of self-consistency. And this is really an attempt to regularize ill-posed inverse problems. In our experiments, as this community will know, we often go from input parameters to output parameters, but we often look at our diagnostics and we ask, what actually happened in that experiment? What were the real parameters that were actually delivered that produced the state that I'm diagnosing and observing? So we prefer models that can go from inputs to outputs. And if I observe these outputs, they go back to the same inputs that we started with. And so this cyclic consistency allows us to regularize these models. It uses less data and increases our ability to make good predictions. Okay, so the question is, does that really work? And it actually does. So the learning system reproduces and recovers key physics information. If you look over here on the left, what we get are integral features that are predicted without explicitly programming them to be present. So here is a strip of true simulation outputs. This on the right is a strip of the prediction using our forward deep neural network models. And you can compare between left and right. You can see that there are features that are similar from left to right. The position in the frame is important. The presence of edges is important. The size of the image in the frame is well matched. There are also some things that it's missing. So in this image over here, you see a smooth transition from dark blue to yellow. And this one, you see a stepwise transition from dark blue to light green to yellow. And that's false. As a subject matter expert, I object to the images looking like that. But what we said at the beginning is that we would give ourselves treatments that allow us to quantify uncertainty as well. So the predicted image also has, along with it, its error map. And if you look at this is a map of the pixel-wise variance. It's black where they're very certain. So in infusing balls of ICF plasma, there are no photons coming from outside the plasma. That's good. If you look at the places where it's bright, those are areas where the model is very uncertain. And those high uncertainties are correlated in ring-like structures, which are exactly the edges that I'm objecting to as a subject matter expert. So the model is saying, this is what I think is going to happen. But for example, if you're relying on these kinds of edges or the absence thereof in your prediction, you shouldn't trust it yet, because this model is not very confident about that. So our predictive tools are really prepared for helping us understand how to use them for going forward with experiments, but really for statistical comparison with that data once we get it. Now we can do realistic Bayesian analysis. So working in this way, combining the data through the autoencoder, it leads to faster training and more accurate models. So engineering this latent space has done one of the things, at least one of the things that we wanted it to do. If you look over here, this is the image loss, or the error that I make in reconstructing images, as a function of mini batch, or the number of times that I've passed through my data, letting the network see it and train on that data. Without an autoencoder, the error falls slowly, and it falls to a level that as a subject matter expert, I'm just not happy with. I wouldn't say that images produced at this level really, to a physicist, look like the images that they were trained on. When we introduce the autoencoder, not only do we get to low loss or better images more quickly, but we get to a level that far outpaces that without the autoencoder. So in some sense, this is just a numerical experiment to show that we've confirmed our hypothesis that capitalizing on correlations and observables can help us improve these models. Now we're using lots of data, And now we know how to train neural networks so that they're not quite so data hungry and we can get to better answers faster. So these new techniques also allow us to use that experimental data that we fought so hard for more effectively. If you look over here on the right, what I have are some posterior distributions, some estimates of input parameters to a model that have been constrained. The inputs to the simulation have been constrained by simulated experimental outputs. So we can get these blue distribution on parameters for the ICF experiment. What they actually are doesn't matter too much. I have the blue uncertainty when I train and constrain my model with just this scalar data. And in ICF, this might be a scalar measurement of the yield, the ion temperature, the time of peak neutron yield, time of peak X-ray yield, et cetera. That blue path gives me the relatively wide uncertainties down here on the simulation inputs. Then I can go another route. I can include not just the scalar measurements, but I can include all of the image data, not just scalar features of it, but all of those. And when I take the orange path of scalars plus images, I find that especially in a few parameters that actually control the asymmetry of my implosion, the uncertainty goes down, in fact, by a factor of 2. So this is another demonstration that we're ready to squeeze everything that we can out of the data. And this is not just a computational thing. This is a statement that we're putting the experimental data that we're fighting so hard for to good use, to reduce our uncertainties and understand how to better model these. And so we put these to use in ICF and other security missions in order to reduce uncertainties on the way we do our model. Interestingly, this helps us quantify the value of new data. So we can ask a question, would it be better to have more images on a single experiment, or would it be better to have more experiments? So shall I build that new diagnostic, or should I save my funding budget and instead invest in more experiments? This is the beginning of a framework to say, what is the value added by the multiple paths I might pursue? So along that same line, doing uncertainty quantification, or UQ, for high consequence applications requires some new capabilities and scrutiny of existing ones. So it turns out that many existing uncertainty analyses are uncalibrated. So what do I mean by uncalibrated? It means if you take a generic deep neural network treatment like Bayesian dropout, and you estimate the uncertainty that your neural network has at reproducing your data, you can generate a 95% confidence interval, and that's fantastic. We wanted to be able to do that. But if you then look at holdout testing data, you'll find that network actually gets the right answer in that 95% confidence interval only 75% of the time. That's not what we mean by 95% confidence. If we were calibrated, we would call that 75% confidence. So our UQ models require validation against actual test data, and it means we need some more parameters in order to tailor all of these confidence intervals. So our team has invented a technique for adjusting the rate at which you can keep or reject fluctuations in the network in order to help you understand what your uncertainties actually are. And so it's really interesting, because at the same time, the UQ framework is not only calibrated, but it's also physically realistic. So we can now have uncertainties between correlated quantities that are actually known to our system to be correlated. So if you look here, most of this audience will recognize that if I have a fusing plasma, the time that I make most of my X-rays, or the X-ray bang time, and the time that I make most of my neutrons is roughly governed by temperature, and so they both have to bang at the same time. Naive models put significant probability on us having bang times in X-rays and bang times in neutrons that are very different from one another, and that's just not physically plausible. So when we go in and calibrate in our space, we at least discover in a mathematical sense, the manifold in which these things should lie in the theoretical world, and we can see that the uncertainties are distributed along that correlated subspace instead of in these places where it's just not meaningful. It's maybe a little more powerful to look at the way that uncertainty propagates into images. Here are a handful of images whose exterior contour at the place where they're starting to get dark is shown here in a family of those things. And I capture over here the innermost one that is most pancake shaped and the outermost one that is most sausage shaped in red. And because we can capture these variations and the correlations from pixel to pixel, we can capture in our uncertainty the variation between the oblateness of the pancake one and the prolateness of the sausage one. if we had not had those correlations, the pixels would all be independently distributed, and these would all have the same identical contour, and we would just see noise that integrated right out of the computation of an integral. So these UQ methods are also widely applicable across science applications and mission spaces here at the laboratory. Okay, so let's do a thing that I'm sort of addicted to doing in talks. I find it fun. The audience usually does. It works a lot better in person than it does virtually, but let's give it a go. So this is some time for some audience interaction, and I won't be able to hear you very well, but please play along at home or wherever you are. So depending on the situation, neural networks can either avoid or inherit human bias. So the point is that learned models know what they're taught and only what they're taught. So humans, even scientists and engineers, can be distracted by context. So let's do a test on ourselves as scientists and engineers. You're going to find the toothbrush in 1 second. I'm going to show you a messy bathroom scene that has bathroom products in it. You're going to be searching for the toothbrush. You got 1 second to do it, and we'll give it a go. So everybody prepare. Look for the toothbrush. Here you go. All right. Did you find the toothbrush? You can just nod to yourself in your room. Oh, good, somebody did. All right. So let me ask, you can unmute. Did anybody find 2 toothbrushes? Let me give you another chance. Here you go. 1, back. Oh, Sabrina found 2 toothbrushes. Okay. For all of those scratching your head about what second toothbrush, let's take a look. Here is 1 toothbrush, which is the one that most of you found. And here is the second one, which most of you will not have found. But somebody has seen the talk before. So sorry, you know the trick. It's very interesting because neural networks find this, and they find this very easily. Humans, not so much. In fact, neural networks can usually find the toothbrush that is shown in the reflection back here. Yeah, Hui sees it. And there's actually a 4th one back here that is the toothbrush that is in the reflection and is partially obstructed. As humans, we screen out the mirror because those are images of objects, and we're looking for objects, not their images. And we also know that things show up at a particular scale, and the toothbrush ought to be about the same size as deodorant. It shouldn't be the size of the entire countertop. We have bias. We've been trained with lots and lots of toothbrushes that toothbrushes do not come in this size. And so neural networks, if they're trained on toothbrushes without a notion of scale, they don't have that problem. Okay, let's do one more of these because they're kind of fun. I like doing it with audiences. You may grow tired of it, but here we go. Is there a parking meter present? Quick one, no. And we go one more. All right, so now ask yourself the question, did you find a parking meter in this urban scene? Some of you will, some of you won't. Here's a 4x scale parking meter. It's very hard for humans to find it, but neural networks do find them with high accuracy. So what's the point? Trained neural networks recognize large targets. Humans often miss giant targets. And that's because expectations, as we mentioned, about scale and some prevent us from finding obvious patterns. But the question here is, what if we've used our simulations to build in bias? We tell our networks that the simulated version of the world is the way that it behaves, even though we know that it is not. The experimental world is the way that it's actually behaving. And so we have to find a way to reconcile that. So what do? Next, we turn to transfer learning to remove simulation bias and better match experimental data. So transfer learning works this way. Let's let the simulation data be blue and the experimental data be red. First, we train the network on simulated data. We turn it completely blue, and now it understands the lay of the land, the general way that our simulators work. If it's a perfect neural network, it's a perfect representation of our, say, rad hydrocode. But that's not good enough because that's not what actually happens in the experiment. So then we can transfer to a new context where we want to get the experimental data correct. We'll keep most of that network fixed, and then part of it we will retrain on our sparse experimental data. The experimental data, say at NIF, is much more expensive. We get much less of it. And so we appreciate schemes where we can get by with less of that data. By retraining the output pieces of the network, I have a model that can understand the theory from the simulation, but make those more precise and accurate predictions of the experimental data that are consistent with the previous observations and empirical measurements that I've already made. So what does this mean? In the ICF context and in other observational contexts, this improves our prediction accuracy. It requires much less experimental data than the initial training process in blue does. And it also measures the discrepancy as a function of input parameters. So I have a naive simulation model. I have a better informed or elevated empirical, partially empirical model, and I can measure the difference between these things as they are parameterized by the input parameters that I've laid out. And hopefully I can go back to the subject matter experts and say, hey, to you EOS or opacity experts, I notice that there's a discrepancy that scales according to these parameters and these powers. Is there a private theory maybe that you have that you were too shy to reveal, or that you hadn't invested a lot of time in because you didn't have a good reason to do it, but now instead of going into 4Pi, you can go in a direction that shows me how it is that my experiments and simulations are different? That's potentially exciting. So transfer learning produces elevated models that incorporate simulation and experimental data to help us make better predictions. One of our colleagues, Kelly Humbert, has offered this example along with lots of others. So we can adapt our learned models to real experimental data in just this way. In ICF, we care about the areal density, or how long we're going to cook our fusion implosion. We care about the ion temperature, what temperature are we cooking it at, and the neutron yield, which is how many neutrons exactly did we cook up. These are plots of the prediction from a class of model compared to experiment. And what we hope is that we target the black y equals x line. The dots represent three different kinds of models. One that is pre-shot, simple 1D physics, and those models you can see do a pretty poor job of capturing this data from our partners at LLE in their 1D campaign. If we go back and do post-shot models, still 1D, but more expensive with cross-beam energy transfer, those more expensive simulations sometimes do a better job, sometimes they get a little bit worse. Not a lot of bang for our buck in the improvement here. In the elevated model, where I take these simulation models and I allow them to be partially retrained on experimental data, we can train on 20 of these 25 yellow dots and then test ourselves on the 5 remaining ones. We find that now we're able to pretty much bullseye the black y equals x line. In most cases, it does a great job, but also importantly, there are some cases where the model fails to land on the y equals x line, but those have gigantic error bars. So the model has told us, either I'm getting this wrong, either because there's not enough simulation data for me to train on, or there's not enough experimental data in this regime, or the experiments and the simulations are in conflict, and so I'm very uncertain. But for whatever reason, let's not trust things that operate here. We can trust things that operate here. So here we've got a single model that holds across all these shots and observables, uses all the data we can get our hands on, and we actually make better predictions. We can do even more complicated things than looking at scalars. In this data offered by Bogdan Kustovsky, our recent CogSim advances can predict not only the scalars, but more challenging images. And so here, if you look, these are some features extracted from the images and actually eventually the images themselves. And you can see in the same mode of prediction versus the ground truth that there is discrepancy in the data in gray in the background before we do our transfer learning with fairly nasty nonlinearities, that upon transfer learning, you are able to predict, you're able to squeeze out and iron out most of those nonlinearities, push yourself back on the y equals x line, and take actual experimental data, use 2D simulations that were actually not very close to the experiment, and you can recover images that are closer in size, brightness, shape, and even have inherited from the experimental data the ability to see things like fill tube features and left-right asymmetries, which are now present in the CogSim prediction, which the simulation was completely ignorant of. This is not done, but it's really exciting and encouraging. We've also adapted these tools to deliver new ICF program capabilities. The bottom line is we have a CogSim model pipeline that corrects a common simulation model using data from all of the existing NIF ignition experiments. So if you look over here at this plot, this is sort of the mean relative error in a variety of diagnostic signatures, neutron yields, burn widths, ion temperatures, you name it. And what you see is a model that's trained on simulations, really cheap, simple 1D whole ROM models of NIF experiments, and then partially transfer learned on each DT NIF experiment that's been done over the last decade. So with a decade of data, I'm able to buy down, really Kelly is able to buy down the error in these observations after a few shots and get much better at using a very simple model to predict what is actually going to happen on DT experiments by capitalizing on what is a relatively small number of shots. But thinking back to the motivating problem that we set ourselves at the very beginning of this talk, what could you do with a facility that was producing data like this, not with 35 shots per decade or 50 shots per decade, but instead doing that every second? There would be transformation if we were able to do that. So this gives us a framework for understanding the ways that we're going to couple the design of experiment that we've done, years or minutes worth of simulation, depending on whether we're in the high rep rate world or the ICF world. We can use all of our historical data and we can make better predictions. And it also gives us a framework where we can go back and take a common model and change the microphysics, things that change the stopping power of charged particles or that change our dependence on equation of state, and look at how they interact over a whole range of NIF experiments, not judging them by just the improved capability to match a single experiment, but instead judging them by the capability to look at an entire corpus of data from an area of high energy density physics that we actually care about. So doing that, though, is reliant on computational capability. And so our newest, largest computers are enabling machine learning at really unprecedented scales. We did a proof of principle demonstration. We generated 100 million ICF implosion simulations, not the highest fidelity Hydra simulations we could do, but a reduced order model that we used to produce a training corpus of 1.5 billion scalar outputs and almost 5 billion images. And then we built the state-of-the-art machine learning solutions that we've been talking about on top of those. And it's really exciting for a couple of reasons. First, because we were able to use one of the third largest supercomputer in the world to train these enormous neural networks, but also because in the process, we developed a shareable scientific machine learning data set that we can share with the science community. So this is great for graduate students in HED who don't have access to supercomputing time. If you want to get your hands dirty with yourself or your students, wherever you are in your career, you can do that here and get access to the data and actually start looking under the hood. The model is open sourced as well, so that you can play around with it and start learning what's going on. I mentioned that we're doing this with the largest machines. So now our lab technologies are operating at singular scales for applied science AI. This is an interesting plot to give us some context for what's going on in the deep learning research world. You can measure an extensive sense of how much training is required in terms of petaflops per second days. This is how many compute cycles are needed to train a model. It's sort of like kilowatt hours in power generation. And look at that as a function of year. And you can see that the amount of compute that's needed has been increasing by doubling every 3.5 months, far faster than we can put transistors down on actual chips. So what we've done is take the laboratory from back in October 2018, where we could train on 10,000 samples, and we've made ourselves able to train on 100,000, then 10 million, then 100 million, eventually working our way up to training for close to an entire Sierra day on the number 3 size supercomputer in the world. And we're starting to make the laboratory competitive with these very large neural networks like AlphaGo and AlphaZero and things that you may have heard of in the popular press. So we can do this at large scale, and we can do it at small scale. And what we're trying to do next is become smart enough that we don't need to literally, and we have done this, parts of our team, literally make the lights dim in Livermore by sucking power out of the grid in order to compute. And now we're going back down this way so that things that used to take us a day on these computers can take us much, much less time. So that brings me to another point, that what commerce wants from next generation computers may not match what we want in science. There's a lot of money, tens of billions of dollars, well beyond that actually, going into AI technologies from a variety of folks who look different than most of the folks who are sitting in this room in terms of their occupations. We are probably more interested in frequent low-cost training than these folks are. They want to invest a lot in an enterprise model, and then they want to evaluate it constantly from every cell phone and every laptop in the world. We want to make hypotheses and changes to them. So we want to do frequent low-cost training and change our model and see what happens when I twist this parameter or the other. And then maybe we're doing less frequent evaluation than they are in a high rep rate laser facility, maybe not. So we're using those data sets that we generated actually to partner with our computer vendor partners to try to make sure that we've got the right computers for the high rep rate laser world, for the ICF world, and for other places, because we don't want these folks to dominate the conversation. They're way bigger than we are, but in one at a time procurements, we buy much bigger machines than they do. So it's an interesting conversation that we're having. For this crowd, I also want to talk about what we're able to do in the computing world with specific physics applications. So our new AI-driven computing methods might change the way that we build computers, because we're changing about the way we think about doing the physics on them. So we can do multi-scale, multi-physics simulations that are super expensive. Here's kind of a diagram of what happens in the hydrodynamics code. We need to propagate laser light, maybe compute magnetic fields, track ions, electrons, do thermonuclear burn, you name it. We also have to do very expensive atomic physics. And in simulations of whole ROMs, that can be half of the computational time expended on computing the radiation field based on the thermodynamic equation of state, or the thermodynamic state. What we can do instead of doing real-time computations of this finite differencing is replace this model with a deep neural network representation trained on copious compute in advance. But when we actually run the code, this code in blue will run on high performance computing at high precision, and the red code will be run as a deep neural network representation that is much faster. And so we're able to bank the high performance computation over here and use it very quickly for the applications that we want to navigate. So we can replace the expensive finite different physics calculation with a fast AI surrogate. And that helps us accelerate. In this case, this will be familiar to a number of you in this audience as well. The atomic physics models are so expensive that if you look at the way that they scale, you can have very simple average atom models that take milliseconds to evaluate, but the physics complexity in terms of the number of levels and transitions that you can represent is pretty low. You can go to very, very complicated models, but that takes days in and of itself. So what we would like to do is go to a physics model that has high complexity, but buy down the time that it takes to do that. And we've shown a proof of principle to do that, where our team has built a deep neural network representation that allows us to learn an atomic physics model. In this case, it's a model that we call Hermit, which is a perturbation of Cretan that you might be familiar with. Then we have a rad hydro code, which is Hydra, that calls the fast deep neural network and gives us, for example, the absorption spectrum. And in whole ROM test simulations, we get a 6.5 times speed up by doing this. So novel processor architectures could help revolutionize the way we train and deploy this kind of model, because this can be computed not on our standard high performance HPC facilities, but it can be computed on specialized architectures. And so here at the laboratory, we've integrated a Cerebras CS1 machine, which is the world's largest integrated circuit. This is, if you imagine a bowl of silicon, a wafer that is the circle that can be circumscribed around this. This is just an entire bowl of silicon with the edges lopped off and then completely filled with transistors. The CS1 is designed to do low precision but very rapid deep learning training and inference. And we've connected one of those to the formerly number 10 fastest supercomputer in the world, the Lassen supercomputer, so that we can do the high performance rad hydro, say with Hydra, on the machine in the background, and we can do the fast neural network evaluation on the Cerebras and pass that information back and forth. And in fact, not only does the neural network architecture speed it up, but going onto the Cerebras CS1 instead of the GPUs that sit on Lassen, you can get a 37 times increase in the rate at which you can pull data through this machine and back into the rad hydro. So there are a couple of ways and levels to increase and accelerate the way that we compute. So here's a final piece of the puzzle before we wrap up. CogSim design optimization strategies are also enabling faster design in rich design spaces that humans can't navigate. Having all of these things that we've talked about, if we think back to the high rep rate laser system, are fantastic, but humans can't look at the data and decide where to go next in the parameter space. And we don't want to specify all of those in advance, because each time we take an experiment, we learn new information that we would like to use to inform the next one. So we need some new methods to optimize complex designs in higher dimensions. And we currently have a team that is working on that. And the idea here is that we will efficiently navigate the space of exploration versus exploitation. So we might sample the corners of this box in parameter space, and find that in the center of that box was the place that I started, and then sample the corners and decide which of these 4 corners is better for my initial guess. It might be this one. And then once I'm here, I'll sample the 4 corners around me, and the best one might be this one. And once I've chosen that one, I'll sample the 4 corners around me. In this way, I can navigate space and get down to a design that I actually like, doing hierarchical investigation along the way. But to do this sampling, I can't afford to run my Hydra simulation at each one of these points. I need a deep neural network surrogate of it. But when I build naive CogSim models or surrogates, they can introduce spurious bumps and wiggles in the surface that when I try to walk this optimization path, push me off to a place that is apparently optimum to this model, but is not actually. So what we need are what we call primed CogSim models that allow us to do efficient exploration and exploitation, but are smoothed out so we don't get lost in artificial bumps and wiggles. And instead we can walk to the local high peak, and then we can zoom in and exploit that region once we've explored to the top of the hill and find that there's actually topography up there, and we can go even further still. So design optimization is going to benefit numerous projects. It's in the stockpile program, it's in ICF, it's in our long range plans, and we're working hard. It's a key feature for enabling the HEDLP thoughts that we have and the exploitation of high rep rate lasers. So I'll end here. Our CogSim leadership has helped capture funding for what we think is an ambitious project in high repetition rate lasers, and I have affectionately called Project Snowball. It was a CIDAC funded in part by the Office of Science, and we haven't always had great success getting funding from them for laser driving, although we have good partnerships with them now. So privately, folks who have experience in the game said you have a snowball's chance in hell of getting this. But because of our leadership, we were able to secure funding and have a very nice partnership now through the CIDAC for this. And we